Hello. This video includes information on Kc to Kp conversions, as well as reaction quotients.
If we look at a reversible reaction that's at equilibrium, the rate of the forward reaction will equal the rate of the reverse reaction. And we can write what's called an equilibrium expression with respect to concentrations of reactants and products. And if we're looking at gases, we can talk about it in terms of partial pressures. So in this particular question, we have a reversible reaction. That's what this arrow in two directions means. So the reactants start to produce products. As the products are produced, they start to reform reactants. The rate of the forward reaction will go down over time. The rate of the reverse reaction will go up over time until the rate of the forward reaction equals the rate of the reverse reaction. The system is then at equilibrium. The concentration of the reactants will be a constant when we're at equilibrium. The concentrations of the products will be a constant at equilibrium, but they don't necessarily have to be equal to each other. So the concentration of the reactants will not necessarily equal the concentration of the products at equilibrium. We call it equilibrium because the rates are equal when we get to that point. So for this particular question, it says the equilibrium constant in terms of concentrations, that's what this C means, equals 0.28 at 900 degrees Celsius. What is Kp, or the equilibrium constant in terms of partial pressures at this temperature? So in order for us to relate equilibrium constants in terms of concentration and partial pressures, we would use this equation here. The equilibrium constant in terms of partial pressures equals the equilibrium constant in terms of concentrations times RT raised to the delta N value. So Kc was given to us in the question. So we would plug in 0.28. There are no units, so just 0.28. For R, we're going to use 0.0821. For T, we want it in terms of Kelvin. It was given to us in Celsius. So 900 plus 273, that'll give us the temperature in terms of Kelvin. So we would multiply these two numbers together. And then we're going to raise them to the delta N value. Okay, where does this come from? It deals with the balanced equation. Okay, it's the total number of moles of product minus the total number of moles of reactant, but only for gases. Okay, if we were looking at a heterogeneous equilibrium that had liquids or solids in them, we wouldn't include it. Kp is only for gases. Now, in this particular case, we're looking at a homogeneous equilibrium because they're all gases. So we have 1 mole of gas here and 2 moles of gas here. So there are 3 moles of gas on the product side. We've got 1 mole of gas here and 4 moles of gas here. So we've got 5 moles of gas on the reactant side. So 3 minus 5 is what we use to get delta N. So 3 minus 5 is minus 2. So we would take 0.0821 times whatever this is, 1173, raise it to the -2 power, and then multiply it by 0.28, we're going to get a really small number, 3.0 times 10 to the -5. And there are no units for Kp, just like there are no units for Kc. And for Kc, oftentimes there's no kind of subscript here. It could say EQ. Okay, oftentimes that's just not, it's just assumed. And C is oftentimes assumed. But P, if you're talking about in terms of partial pressures, that has to be there. What does K actually mean? K is an equilibrium constant. And if K is a really big number, okay, like 10 to the -5, which is a really, really big number, it means that when the reaction reaches equilibrium, it's mostly product, which means that the reaction proceeds to produce a lot of product and consumes almost all of its reactant before equilibrium is reached. We would say that the equilibrium lies to the right, or it lies towards the product side. Essentially, if the K value is super big, it means the reaction almost goes to completion. So when we calculate K, if K is the concentration of the products raised to the power of the coefficient in the balanced equation, over the concentration of the reactants raised to the power of the coefficient in the balanced equation, the only way K can be a really, really big number is if the products are big and the reactants are small. Now, on the other hand, if our equilibrium constant is really small, like let's say 10 to the -5 or even less than that, it means that when that particular system reaches equilibrium, it's almost all reactant. It produces very little product before the system actually achieves equilibrium. And we would say in this case that the equilibrium lies to the left, or lies on the reactant side. Or the reaction really doesn't occur to a very significant extent at all. We don't produce much product at all. So when K is a small value, it means we have very little product at equilibrium, and we have mostly reactants at equilibrium. Now, we have another value that we can calculate called the reaction quotient. The symbol that's used for that is Q. And what Q can do is it can tell us whether we're at equilibrium. Have we reached equilibrium yet? And if we haven't reached equilibrium, will the forward reaction rate be greater, or will the reverse reaction rate be greater to get to equilibrium? So to calculate Q, we would take the values that were given in the question. They may or may not be equilibrium values, but they're the values that are given to us. And then we can figure out whether or not the reaction's at equilibrium or not. And if it's not at equilibrium, are we going to be shifting to produce more product or more reactant to establish equilibrium? So let's say that we have K and Q is smaller than K. That means that we have too much reactant and not enough product. This number is too small. The system is going to spontaneously move towards equilibrium. So we want to increase Q to get to K. So the reaction is going to shift towards the right. it's going to shift to consume reactant and produce product. And in doing so, Q will get bigger and bigger as the product values increase and the reactant values decrease. And eventually, Q will equal K and will be at equilibrium. So here's one scenario. Now, maybe we calculate the values we're given and it equals K. Well, if that's the case, we're at equilibrium. We're not going to have any shifting to the right or shifting to the left or producing more reactant or producing more product. The amount of reactant will be a constant and the amount of product will be a constant because we're already at equilibrium. Now, our third scenario is if Q is bigger than K. If Q is bigger than K, we're not at equilibrium because Q has to equal K to be at equilibrium. We're not at equilibrium. We want to decrease Q to get to K. Well, if Q is too big, that means we have too much product. So we're going to want to decrease product and increase reactant, which means the equilibrium is going to shift towards the left. Now, as this happens, the products go down, the reactants go up, Q becomes smaller and smaller until eventually Q equals K and the system's at equilibrium. So we'll be given questions where we're given K, we're given the equilibrium constant, and we're given some concentrations, and we're asked really essentially two questions. The first question is the reaction at equilibrium? So we calculate Q, and if it's equal to K, we're at equilibrium and the problem's over. But if Q doesn't equal K, which way is the reaction going to shift? If Q is less than K, it's going to shift to the right. If Q is more than K, it's going to shift to the left. Okay, so let's apply this. So we're given a reaction here. The arrow in two directions tells us that we have a reversible reaction, which will spontaneously reach equilibrium. In the question, it tells us that we have 0.0500 moles of NO2 and 0.100 moles of N2O4 in a 1 liter container at 25 degrees Celsius. Now, the temperature really has nothing to do with the question. As long as we don't change the temperature, it doesn't matter what the temperature is. We're given K. We want to calculate Q and compare it to K. Now, we calculate Q essentially the same way we calculate K. So the first thing we do is we write down our Q expression. Okay, it's the concentration of the products over the concentration of the reactants raised to the power of the coefficient in the balanced equation. So we've got a 1 for our product. So there's a 1 that's assumed to be here. And we have a 2 for our reactants. That's why it's raised to the 2 power. We write a Q expression the same way we write a K expression. The difference is K is at equilibrium. Q may or may not be at equilibrium. Concentrations are molarities. Molarities are moles per liter. Now, this question is kind of easy because we're looking at a 1 liter container. So the number of moles is just being divided by 1 to get to the molarity. So we would plug in our molarities. So 0.1 moles per liter of product, 0.05 moles per liter squared for our reactant. So 0.1 divided by 0.05 squared tells us that, Q equals 40. Okay, so now we need to ask ourselves, is this system at equilibrium with these values in the container? And we do that by comparing Q to K. So K was given to us, okay, 1.7 times 10 to the second power, which is really 170. So 170 compared to 40. That means our system is not at equilibrium because these numbers are not equal to each other. In this case, Q is less than K. Now, K can't change. K is a constant. Q can change as the concentration of the substances in the reacting vessel changes. So we want to increase Q until it's equal to K. Well, in order to increase Q, that means we're going to have to increase product and decrease reactant. In order to increase product and decrease reactant, the reaction is going to shift in what's called the forward direction, or it's going to shift towards the right. As we increase product and we decrease reactant, Q is going to become bigger and bigger. And eventually Q will equal K, and the system will have achieved equilibrium. So when we're given a question like this and it says, are we at equilibrium? We write a Q expression, products over reactants raised to the power of the coefficient in the balanced equation. We plug in the concentrations, we calculate Q and compare Q to K. Are we at equilibrium or not at equilibrium? And if we're not at equilibrium, which way will the system shift? So let's look at another problem, very similar to the first problem, except there's just a little bit more maybe work we have to do. So if we were to look at this question, we're given the reaction. We've got nitrogen gas reacting with hydrogen gas to produce ammonia. It's a reversible reaction which will achieve equilibrium spontaneously. We have a 50-liter container, and it has 1 mole of nitrogen, 3 moles of hydrogen, and 0.5 moles of ammonia. In which direction, towards the reactants or towards the products, will the system shift to reach equilibrium? And it gives us K equals 0.500. All right, so what we're going to need to do is write a Q expression, calculate Q, and compare it to K. But here's why this question's a little bit different. We don't have a 1-liter container like we had in the last question. We have a 50-liter container. So what we're going to need to do first is calculate the concentration of nitrogen, hydrogen, and ammonia before we can plug it into our expression. So how do we do that? Well, the molarity of nitrogen, or the molarity of anything, is moles per liter. So for nitrogen, we have 1.00 moles in 50 liters. So the molarity of nitrogen is 0.0200. Oops. So using this as a model, calculate the concentration of hydrogen and then calculate the concentration of ammonia. Make sure you show your work. Okay, I did have some people that weren't showing all their work and then did some silly mistakes here and there thinking they could do some mental math, and that didn't help very much. So make sure that you really show your work logically as you possibly can. It absolutely helps. Okay, I agree. Now just watch your significant digits. So 0.0600, since there's 3 digits here and 3 digits here, we want 3 digits here. Remember that these 2 zeros are placeholders. So the 6, the 0, and the 0 are your significant digits. Okay, and then for ammonia, 0.0100. Again, you want to show 3 significant digits to show, that's how many significant digits are in the measured values. So now we have the molarities, our concentrations. So the next thing we want to do is we want to calculate Q. So write your Q expression, products over reactants, raised to the power of the coefficient in the balanced equation, and then get your value for Q. Now, be careful of the coefficients, right? You're raising the concentration to the power of the coefficients in the balanced equation. So ammonia squared over nitrogen and hydrogen cubed. Okay, if you don't use the coefficients in the balanced equation, you're not going to get the same answer. Okay, write down your Q expression and then plug in the numbers. Be careful with your order of operation in your calculator and see what you get. Okay, so you're going to have to put in your calculator 0.01 squared divided by 0.02 and divided by 0.06 cubed. We're not going to cube everything. We're just going to cube the hydrogen part of it. Okay, so nitrogen's to the first power, hydrogen's to the third power, ammonia's squared. So we want to write that Q expression, plug in the numbers. Be careful with that order of operation. Okay, and since we've got 3 significant digits, we want to write 3 significant digits there. So 23.1 would be Q, and there are no units. All right, so what are we going to do with that now? Well, here's the value for the concentrations that are in the vessel. K tells us what that ratio would be at equilibrium. K and Q are not the same number. That means the system is not at equilibrium. Well, K can't change. As long as we don't change the temperature, K is a constant. Q is the value that will change. And we're going to want to make Q smaller in order to get it to equal 0.5. Well, if Q is product over reactants, and we want that value to go down, the products are going to have to go down and the reactants are going to have to go up, which means that system is going to be shifting towards the left, or it's going to be shifting towards the reactants. So the concentration of the products will go down. The concentration of the reactants will go up. Q will get smaller and smaller until eventually Q equals K, and then the system is at equilibrium. And once the system gets to equilibrium, the concentrations of reactants and products will become constants. They won't be equal to each other, but they'll become constants because the rate of the forward reaction will equal the rate of the reverse reaction.